Welcome back to ROBT402 Robotic Mechatronic System Design course, Lecture 7 Programmable Logic Controllers or PLCs. Today's topics are as follows. Define Programmable Logic Controller, PLC. Identify the main parts of a PLC and describe their functions. Outline the basic sequence of operation for a PLC. Identify the general classification of PLCs. Overview of schematic ET 200 SP CPU 1512 SP-1 PN. Programmable logic controllers are now the most widely used industrial process control technology. A PLC is basically a digital computer designed for use in machine control. It has been designed to operate in the industrial environment and is equipped with special input-output interfaces and a control programmable or programming language. So PLC is nothing more than a digital computer specialized for industrial environment with specific input-output interfaces. Initially, the PLC was used to replace relay logic, but its ever-increasing range of functions include timing, counting, calculating, comparing, and the process of analog signals. The structure of a PLC is based on the same principles as those employed in computer architecture. So this is a laptop or a personal computer, PC, and this is a PLC. So the main structure is the same. They have a CPU, a processing unit, and again, a PLC is just a specialized computer for industrial environment, and it's designed to replace relay logic and relay controllers. So before PLC, they've been using relays to design a logical circuit, and nowadays those relays are replaced with PLC, excluding some specific cases. So relays are still in use, but very limited for specific cases where it's safer to use relays instead of PLCs. Programmable logic controller advantages. So when we say advantages, we are comparing PLCs, this is PLC, with a relay circuit. So this is a relay control panel or relay circuit, and this one is a PLC control panel. So what is the main advantage? So we are replacing PLC. Again, remember that PLCs are aimed to replace these type of circuits. What is the main advantage? Elimination of much of the hard wiring associated with conventional relay control circuits. So you see that we have lots of hard wiring here, and all of these wirings and relays are replaced with this PLC. So the rest of the circuit is basically has nothing to do with the logical circuit, and this whole circuit now is basically compacted into the PLC. The next advantage is increased reliability. Since all the logic is contained in the PLC's memory, there is no chance of making a logic wiring error. So again, because we eliminated those wirings, and all of those wirings are now a program inside PLC memory, So the reliability is much higher because there is no chance of basically disconnection in any of those hard wires. The next advantage is more flexibility. It is easier to create and change a program in a PLC than to wire and rewire a circuit. So this is a ladder logic, one example of ladder logic PLC a program based on, so this is a program based on the ladder logic language, and you see that this program is replaced by all of those wirings, and since we don't have the hard wiring, it's easy to change the basically the language and again download it to the memory of the PLC. But if we want to change the logic in a relay logic circuit, we need to basically change all the wirings. Lower cost. Generally, if an application has more than about a half dozen control relays, so half dozen is 6. So if one application has more than 6 relays, it will probably be less expensive to install a PLC. So when they have more than 6 relay, it's cheaper to have a PLC. Communication capability. A PLC can communicate with other controllers or computer equipment to perform such functions as supervisory control, data gathering, monitoring devices, and process parameters, and download and upload of programs. So PLCs could communicate with each other plus with field devices. So we have this capability, but of course relay circuits don't have this communication capability and memory or data gathering and etc. Another advantage of PLCs over relay circuits is faster response time. Machines that process thousands of items per second and objects that spend only a fraction of a second in front of a sensor require the PLC's quick response capability. So you see that these items are passing by, and here we have a sensor. So the sensor needs to basically send a signal to the PLC. Okay, so if we increase the speed of this conveyor here, the sensor is sending signal with the higher frequency to the PLC. So PLCs usually have a faster response time, and they could cope with the high frequency data coming from the sensor, but relays have a less response time compared to PLCs. Another advantage of PLCs over relay circuits is easier to troubleshoot. To find and fix problems, user can display the control program on a monitor and watch it in real time as it executes. So here we have a PLC, and let's say the PLC is already basically a program is already downloaded on the PLC. So there is a program on the memory of PLC, and the PLC is running and is controlling the system, the process. So we could monitor the functionality of the program on the screen. So I could see what's going on step by step on the screen. So of course, for simple logic circuits, maybe it's also easy to work with relay circuits, but when the program or the logic becomes more advanced and complex, then it would be very tough to monitor or troubleshoot the errors in relay circuits. Okay, so far we know basically the very basic fundamental of PLC and what are the history behind the PLC that we are using them to replace basically relay circuits. Now we want to talk about parts of a PLC. So here we have a PLC. The major parts of a PLC system are the central processing unit or CPU, the input-output or I/O section, the power supply, and the programming device. So as you could see, there is a huge analogy between a PLC and a PC or a laptop. We have this CPU here, central processing unit. We have input module, we have output module, we have a power supply module that provides power, or basically a desired voltage and current to a CPU and input-output modules. And we have also the memory, and on the memory we have a program and the data. So the input module is connected to all the field devices. For example, here we have three types of basically switches and sensors. We will discuss these symbols as we go forward through the course. Plus the output module is connected to output field devices, let's say a motor or a pilot light or the horn or the solenoid and so on and so forth. So the input module is connecting data from the input devices, including switches and sensors. You will send it to the CPU, and the CPU will process the data based on the program on the memory and will update outputs. How we could change a program on a PLC? We need to connect it to a laptop or PC, which has a proper software for interfacing with the PLC, and then we could download or program from the PC to PLC. The term architecture can refer to PLC hardware, to PLC software, or to a combination of both. Okay, so we have architecture for the hardware and for the software, exactly same as personal computers. An open architecture design allows the system to be connected easily to devices and programs made by other manufacturers. Okay, so here we want to discuss open architecture and closed architecture. Okay, so what is the definition of open architecture? Based on the definition, open architectures could communicate. Okay, so could communicate with other devices or programs which are made by other vendors or manufacturers. A system with a closed architecture is one whose design is proprietary, making it more difficult to connect to other systems. So, for example, Siemens PLC architectures are closed and they could only communicate with their own software. And for example, the Codesys program or PLC program is an open architecture one and could communicate with devices from other vendors or manufacturers. Fixed input output or fixed I/O is a typical of small PLCs that come in one package with no separate removable units. The processor and I/O are packaged together. So here you could see lots of these type of fixed I/O PLCs, and you see that a CPU memory communication input module or section and output section or module and power supply, all of these parts are integrated into one system or box. And you could see, for example, here one of those fixed I/O PLCs that we could connect input field devices to output field devices to the PLC and program the PLC. Of course, in these type of systems, the number of input outputs are limited. Usually, basically, capability of or characteristics of these PLCs are lower than modular ones, but anyway, they are very good for educational purposes and some type of industrial systems. Modular I/O is divided by compartments into which separate modules can be plugged. This feature greatly increases your options and the unit's flexibility. So here you could see one PLC. Here we have the power supply. The next module or section is the processor module or CPU, and then we have input and output modules. So we have a rack. Okay, so here is a rack, and we could install or input and output modules. Okay, so here you could see one industrial sample. We have a power supply unit, the processing unit, and then we have input output modules. So see that we have a greater basically option and the flexibility. So in case we need more input to the system, we could add those modules. For example, if we need, for example, analog input, we could install an analog input module, and basically we have this flexibility and options to change the configuration of the system. The power supply provides DC power to all modules that plug into the rack. For large PLC systems, this power supply does not normally supply power to the field devices. So for the MPS 500 case, the power supply of the PLC provides power to all the field devices, but for some industrial applications, of course, the power supply of the PLC is not strong enough to provide power to all field devices, and they have basically a separate power supply unit. The processor CPU consists of a microprocessor for implementing the logic and controlling the communication among the modules. So CPU basically gets input data and updates the output modules and do the processing based on the program on the memory. The processor requires memory for storing the results of the logical operations performed by the microprocessor as well as the operating system and the PLC program. The PLC program is executed as part of a repetitive process referred to as a scan. So here we have a scan cycle, or that repetitive process that goes continuously. Starts with the CPU reading the status of all inputs. So CPU gets the input status or updates from the input module. Then we have basically execution of the program. So the PLC execute program based on the provided input. Then we have diagnostic and communication. And then finally at the end we have updating output. So concludes with the updating of all outputs. And then again it goes on and on, and usually the frequency of this cycle is high. Okay. Let's say 1000 Hz and more. The I/O input-output system forms the interface by which field devices are connected to the controller. So here we have an input module, and here we have some field input devices. So input devices such as push buttons, limit switches, and sensors are hardwired to the input module terminals. Okay, so we have some limit switches and push buttons and basically limit switches, and all of these are connected to the input module. And for example, in this case we could have 16 inputs. In case more than 16 inputs are needed, for example we have more than 16 input field devices and sensors, then we could add one input module to the system for the case of modular PLCs. And the same goes for the output module. Here we have one output module which is connected to some output field devices like a motor, solenoid, and pilot lights, red and the yellow pilot light. And you see, for example, here the field device power supply is separate because the field devices here works with 240 volt AC. Okay, and the output module here is also 240 volt AC. Okay, so that should also match with the field devices. Output devices such as motor starters, solenoid valves, and indicator lights or pilot lights are hardwired to the output module terminals. A programming device is used to enter the desired program into the memory of the processor. Okay, so here we will discuss two types of programming devices. The first one is handheld programming device. So this is a portable programming device. Of course, we don't have that flexibility we could have on a PC or a laptop because you see that the screen is small and the keyboard is not that comfortable. But for some cases in industrial companies, since basically devices are far apart from each other, and operators need to change the PLC program routinely, then we could use these type of handheld programming devices. But in those cases, the operator, of course, doesn't do much of complicated changes to the system. Very simple, basically changes. For example, if they want to change, for example, the coding system. Okay, for example, there is a stamping machine, and the stamping machine or barcoding machine, and that works. And there is a program already on the memory of the PLC, and the operator, for example, needs to change that dating system. So they use these type of handheld devices, okay, for a limited changes, I could say, okay, or going through the option and checking one option or choosing one option. The next programming device is just a laptop or PC. The program is entered using the relay ladder logic programming language. In this case, on this basically picture, in this picture, we are using relay ladder logic programming language because this is the widely used or most common basically PLC language. But we could of course use PC or laptops to program or PLC with any other type of programming languages. A personal computer PC is the most commonly used programming device. So here we have, let's say, RS Logic 5 program for Allen Bradley PLCs. This is a software, this is a programming environment, and in this picture they are using also ladder logic programming language. The computer monitor is able to display more logic on the screen, thus simplifying interpretation of the program. So you have more basically screen and wider screen and more flexibility to go through the options and program or PLC or monitor or troubleshoot or program. So what is a program? A program is a series of instructions that directs the PLC to execute actions. Okay, here we have one example. Relay ladder logic, the standard programming language, is based on electromagnetic relay control. So at the beginning of this lecture, we said PLCs are designed to be replaced by relay circuits. Okay, so if you could see here, we have some contacts and coils, and these contacts and coils, they represent relays. we call them instructions. So these contacts and cores, we call them instructions. We have a variety of these type of contacts and cores. We will discuss them in coming lectures. And each line is basically, we call each line a rung. Okay, so rung connects input to the output. And on each rung we could have some branches. We basically will have a separate lecture on ladder logic programming language. So we will discuss basically the ladder logic program in more detail later. Principles of operation. Okay, so here we have a double acting cylinder control program, and here is a relay control system. We don't have any PLC. So far you have studied pneumatic circuits, so you should be familiar with this pneumatic circuit. And on this pneumatic circuit we have two solenoid, is one M1 and one M2. Okay, and we have two sensors, one B1 and one B2. So one B1 and one B2 you could see in the electrical circuit. All of these are basically designed and programmed in FirstFloyd C. You could replicate the same circuit. I will provide the circuit to you on Moodle, so you could learn from that example how you could add electrical circuit and sensors and solenoids to your pneumatic circuit. So here we have two sensors, one B1 and one B2, and we have basically three solenoids, K1, K2 and K3, and those solenoids are used to we have three relays, K1, K2 and K3. So those relays are used to basically provide a logical circuit here and controlling one M1 and one M2 solenoids. So you could see that we have K1 and K2 and K3 relays on the circuit. Once the K1 and K2 both are closed, then one M1 will be energized. Once the K3 is closed, then one M2 will be energized. Okay, so for the case of K3, when we have an input from the sensor, once the basically 1B2 is active, then the K3 relay will be active and 1M2 will be energized. For the case of K1 and K2, so you see that we have two switches here, S1 and S2, and one of them is start, the other one is stop. And once basically the start is pushed, okay, once the start is pushed plus, see that we have K2 here, and we have signal from the sensor 1B1. Okay, so once the start is basically pressed, then the K1 will be on. Once we have 1B1 signal, K2 will be also on, And you see that we have K1 and K2 in series, so it means that both K1 and K2 should be on. So it means that we have an AND logic here to energize M1. Okay, here is a PLC control system. The previous system, the same pneumatic circuit we had, now is replaced with a PLC. What is the language in the PLC? The programming language here is not the basically the logic programming language, and is a basically graph language. Is a different language that we will discuss. Okay, anyway, we have a programming language inside the PLC. We have inputs, we have field devices. You see that we have field input devices. Okay, field input devices are here, connected to input module. You see that we have I1 to I8. These are inputs to the system, so this PLC could accept 8 inputs and could have 8 outputs. So we have input field devices. What are those devices? Sensors and switches, start and stop switch. And we have output field devices. What are those ones? Are solenoids. So the PLC will be provided by the input data, and it will process the program. Based on the program, it will update the output field devices status. I will provide you with the first deployed sim file for these slides on Moodle. So you could open it and simulate it. Plus, you could inspire from that file to understand how you could program and design electrical circuit or PLC in Festo Fluidsim. Okay, so let's go with an example. We have a mixer process control problem. Here is a device. We have our mixer. The mixer has a motor, and we have a pressure sensor switch here. Okay, and we have a temperature sensor switch. So both of these switches or sensors are input to the system. This is a pressure sensor. This is a temperature sensor. Okay, and we also have another input, which is a manual push bottom station. This is push bottom station. Okay, so we have 3 inputs and we have 1 output, which is the motor. Okay, so a mixer motor is to be used to automatically stir the liquid in a bath when the temperature and pressure reach preset values. Okay, so you should have both of them reach the preset value. Manual operation of the motor is provided by means of a separate push bottom station. Okay, so let's see how we could program it. Okay, so here is a relay circuit. So pressure sensor switch and the temperature switch, both of them should reach to the preset value. If that happens, then the motor starter coil will be energized and the motor will start. What is the voltage? Is 120 volt AC. Or we could manually start our motor by the manual push button. So you see that we have two branches. They are parallel to each other. Either this line or this line could provide a continuity or a logical continuity for the motor starter. Okay, very intuitive circuit. Yes. The motor starting coil M is energized when both the pressure and temperature switches are closed. Or, so you see that here we have and because they are in series, or because we have two parallel branches, or when the manual push button is pressed. In any of these cases, the motor will start. Okay, PLC method for control of motor. Now, we discuss the hardwiring and relay circuit, but what about the PLC method? The same input field devices, pressure switch, temperature switch, and push button are used. So these field devices now are connected to the input module of the PLC. And field devices are hardwired to an input module. Okay, so this is the input module. And in this case, the input module could accept 8 inputs. And the input module type is 120 volt AC also. Okay, this is a digital input module. Okay? We don't have any analog input to the system for this case. For the output module, the same output field device, motor starter coil, is used. So we only have one output, and that output is connected to the output module of the PLC. And the starter coil is hardwired to an output module. This is the output module of this specific PLC in this example. Okay, now that we connected our input and output field devices to the PLC, now we need to program the PLC. Okay, so this is the program inside the PLC. We don't have a hard wiring as we had in previous slides between the input and output module. The interface between these two are based on the PLC or provided by the PLC. So here we have a ladder logic program. So you see the ladder logic program is very similar to the hard wiring of the system in relay circuit. So we have two contacts here, which are a pressure switch or sensor and temperature switch or sensor. And this contact has an address of I1, and the pressure sensor is connected to the first input of the input module. Okay, and the same goes for the second one. And also we have a manual push button which has the same address of the as the push button I3, and we have one output, and we call the output here coil. And since the starter coil is connected to the first the first port of the output module, or O1, so the coil also should have the same address. So now the motor starter will start if the pressure sensor or the temperature sensor switches are on or are true. Or alternatively, if the manual push button is pressed, so this contact status will be true or on, and the motor starter coil will be true. The symbols represent instructions and the numbers represent the instructions addresses. Okay? So this is symbol, this is numbers. Okay, each input and output device is given an address which lets the PLC know where it's connected. Okay? So for example, if we change the address to I4, okay, so since the force port of the input module is not connected to any devices, then the status of this contact always will be false, okay, so it won't be updated. For the program to operate, the controller is placed in the run mode. Okay, so the PLC should be in a run mode. During each scan, the controller examines the status of input devices, executes the user program, and changes output accordingly. The coil O1 is energized when contacts I1 and I2 are closed or when contact I3 is closed. Either of these conditions provide a continuous logic path across the rung that includes the coil. So you see that if both of these are true, we have continuous logic path, or if the manual push button is pressed, we have continuous logic path in the rung. So here is the rung, and on this rung we have two branches. Typical wiring required to implement the process control scheme using a fixed PLC. So here is a fixed PLC, and we have the same input devices as the previous example, and you see that are connected to the I1, I2 and I3. Plus for the output, the motor starter coil is connected to the Q1. Okay, what do we have inside the memory? We have our program based on the ladder logic program, and you see that when the I1 and I2 both of them are correct, then the Q1 will be true or on, or alternatively, if the I3 is on, the Q1 will be on. PLC size and application. The criteria used in categorizing PLCs include functionality, number of inputs and outputs, cost, and physical size. The I/O count is the most important size factor. In general, the nano is the smallest size with less than 15 I/O points. This is followed by microtype, 15 to 128 I/O points, medium types to 512 I/O points, and large types over basically about 500,000 I/O points. Matching the PLC with the application is a key factor in the selection process. So we need to see how many input outputs we have, and then based on that we need to select the size of our PLC, or basically the size of input outputs. Okay, so see if the rack of the PLC could accept enough input output modules which match our application. There are three major types of PLC applications: single-ended, multitask, and control management. A single-ended application involves one PLC controlling one process. So for the MPS 500, this is exactly the case. For each process on each station, you have one PLC, and this is a single-ended application. Multitask PLC application involves one PLC controlling several processes. Okay, so it's more central. PLC adequate I/O capacity is a significant factor in this type of installation. So that PLC should accept a large number of input-outputs. A control management PLC application involves one PLC controlling several others. Okay, so we have, let's say, one central PLC that communicates and controls other PLCs on other processes and stations. This kind of application requires a large PLC processor designed to communicate with other PLCs and computers. The control management PLC supervises several PLCs by downloading programs that tell the other PLCs what has to be done. Okay. Now let's talk a bit about instructions. The instruction set for a particular PLC lists the different types of instructions supported. So I could say that most PLCs these days support basic instructions. However, for more advanced instructions or number of input outputs or frequencies, then type of PLC will come in place, and we need to consider that. Okay, so here we have some XIC examined on or XIO examined off, OTE, output energize, output latch, timer off delay, timer on delay, countdown, count up. We'll discuss these instructions in coming lectures, don't worry about that. But for the purpose of this slide, we want to say that not all PLCs will support all type of PLC instructions, and that would be a factor in choosing our PLC. Okay, now you should be able to define the programmable logic controller and mention its advantages, identify main parts of PLC, outline the basic sequence of operations for the PLC, and identify the general classifications of PLCs. Okay, at the end of this lecture, we'll go through schematic ET200 SPIS CPU, which is a Siemens PLC that we have on MPS 500 system. And this is exactly the reason we go through that, because we have it on the MPS 500 system. You may not be able to particularly use this PLC with the hardware because we don't have access to the lab. However, that would be a great example for learning and understanding the structure of PLCs. Okay, so where did I get this picture? From the TIA portal. In the TIA portal, which is in for programming and communication with Siemens PLCs, there is one section for designing and choosing the hardware. Okay, so we selected this schematic ET200 SPIS CPU, and we added 2 input modules and 2 output modules. Why exactly 2? Because we want to match our program with the real hardware that we have on MPS 500 systems inside the lab. Inside the lab, PLC has equipped it with 2 input modules and 2 output modules, each accept 8 inputs or outputs. Digital input module with the 8 input and 24-volt DC. And for the output, digital output, okay, so in PLCs, instead of always use Q to avoid confusion with 0, so that this means digital output, and this output module could accept 8 digital output ports, and it has 24-volt DC. Plus also we have a server module, and that server module is aimed for the communication. So this is our PLC. The rest of these racks are empty. It means that we don't have them in the real system. So let's see how does it look like in reality. Here is the PLC and the power supply, both unit and the memory unit. So you could see that we could have these external SD cards. So some of the technical properties, I won't go through the whole detail, but for communication interfaces, the CPU has a Profinet interface. Profinet is basically a standard protocol for PLC communication and could accept 3 ports, so it has very similar ports to the LAN port of computers. Integrated web server. And what is the web server? We can read out some information with the web server. Integrated technologies are motion control, integrated closed loop control functionality, PID compact, PID 3-step, PID temp. So these are capability of these PLCs and features that you could use. Has trace functionality, integrated system diagnostics, and integrated security. We'll go through some of these properties, and you will learn about some of these properties as we go forward into this course. Okay, so here we have a front view of the module with bus adapter. Let's see what we have here. Okay, so we have nice numbers here. It shows we have a mounting rate release. It's basically for releasing the module from the mounting rack. On that rack also we could have input-output modules. We have okay, so labeling strips just to attach a label or a paper here. LEDs for the status of the system. So here we have basically run, stop, and memory line, and LED indicators. The combination of them means something. Okay, it means if the system is running, stop, or there is an error in the system. Here you could see the SD card. You could see that 1 and 2 of the ports or Profinet ports. Here is another Profinet port here. Okay, so overall the system could accept 3 Profinet ports. We have some other basically here 5 is a mode switch. For example, we could put the system on run or stop it. 4 is the LED indicator that displays the supply voltage if we have supply voltages on. We have some other details, but I think it's not necessary for the purpose of this slide and this lecture to go through the whole details, but you could study them by yourself. So for example, we have run, stop, and MRES, or memory reset LEDs, and when the system is running, the CPU is executing the user program. So the run LED is a green LED. Stop mode is a red LED that shows the user program is not being executed, and the memory reset position for CPU memory reset. Okay. There are more details into this combination of these LEDs and indicators. Okay, so LED displays, we have run stop LED, a yellow green LED. Okay, we have error LED, we have maintenance LED, yellow LED, or also they call it memory LED. Okay, it's just a name, but we should defer to the instruction of the PLC, because combination of them could mean different stuff. We have link RxTX LED for ports X1, P1 and X1, P2. So for example, if the port P1 is connected, then the LED of that port will be on the power LED. Okay, the power LED shows that the PLC is provided with the proper power, and the link RxTX LED for port X1, P3. Okay, this is that port, and this is the LED. It means that this port is connected, for example, to a laptop, or to a personal computer, or any other devices. Okay, so if this port is used, that LED is on. So this is the last slide of this video, and we could conclude our discussion here. And the whole lecture we discussed basics and fundamental of PLCs, and it was introduction basically to a PLC. What is PLC in terms of hardware, software, what was the story behind